Thank you, German. Thank you, Stefan, for having us here. Before I begin talking about magnetic origami, I would like to acknowledge the two people that do most of the work. It is Safir and Emily, two PhD students that graduated from school. I should also acknowledge that this work in collaboration between SpinTech and Miron Institute in Grenoble. So let me start by the outline. I'm going to show what I hope is a new concept of adaptive magnetization switching. Then I will show you results, experimental results, non-collinear domain motion, and based on this, I will show how we build what we call magnetic origami. Just to begin, this is a very simple movie. It's a magnetization switching, trivial magnetization switching driven by a magnetic field. So what's noticeable here is that despite the fact that the magnetization switching is completely non-uniform and very complex, the excitation is actually very trivial. It's just a uniform magnetic field constant in time. So what we thought was, what happens is instead of applying a constant perturbation, trivial one, we would have one that just like the magnetization, it is also a function of space and time. By doing this, we can expect to improve the switching behavior and perhaps even obtain exotic behavior. Okay, so the two ways of acting on the magnetization using electric currents, you all know all of them. One of them is using spin transfer torque, where you transfer angular momentum from one layer to the other. And the other one is using spin orbit torque, where the electric current is spin polarized by the spin orbit interaction. So both these phenomena have been shown to switch in plane and out of plane magnetization. Okay. There's a spin orbit torque that I'm going to focus on. We know that it is very large in ferromagnetic heterostructures made of ferromagnetic thin film and a heavy metal. We don't really know if it comes from the interface or the bulk. But anyway, we know that what the basic ingredients are. From the point of view of engineering, if you want to make memory, you should know that in both cases you read using the TMR, so you use a vertical current for reading, but in one case you have the same current path for writing, while in the other you have an in-plane current for writing. Which means that this is a two-terminal device, where this will work as a three-terminal device. So what does it actually mean? As you can see here, I put a terminate. So the first thing you can notice is that in this configuration, because the three-terminal device, the free layer and the reference layer are no longer, they don't need to have the same shape. So you can have the free layer which has a different shape with respect to the reference layer. But the real important thing is that this is a three-dimensional object. So then, this means that you can basically give any shape to the free layer and any direction of the electric current. And this way, you can hope to have different magnetization switching schemes, just by playing with the shape. And this is what I want to show next. So how does it work? I'm sorry for the contrast, it's not very good, it was better on the screen. So you have all the elements separated here. So you have the contour of your non-magnetic layer, which together with your applied voltage gives you the distribution function and the time dependence of the electric current density. This one together with the contour of your ferromagnet will give you the distribution of the torque inside the ferromagnet. Okay? So the goal is to match the torque in the ferromagnet to the magnetization dynamics, so that you obtain the behavior that you desire. Okay? So as a real system, we use platinum, cobalt, aluminum trilayers. These are very thin cobalt films grown on platinum and covered by aluminum oxide. In reality, the switching is not extremely complex. It's basically dominated by nucleation and propagation of domino motion. So the first thing we want to study is the domino propagation under electric current. But this is not as trivial as what has been done before. where people only studied domain motion in the direction of the electric current. Here we need to take into account all the possible orientation between the current-induced domain motion and the electric current. So for this reason, we make this kind of structure. We have a platinum pad, which is slightly wider and longer, connected to a voltage here. And you have the aluminum, the cobalt aluminum magnetic part, which is smaller and has a hand-like shape. We made this like this, so we have propagation directions which are different, while the current is only flowing in this direction. Okay? As a tool to study this phenomena, we used wide field Kerr microscopy, and here you have a differential wide field Kerr image, where you can see that only the fingers are magnetic and the pad is entirely non-magnetic. I remind you that the differential image is just made by subtraction of two images before and after, so you don't see any topological contrast. So what happens when we apply current? First, we place domain walls using the magnetic field in each of the wires, apply positive current. Once again, the differential contrast shows the displacement of the domain walls. So you can see they move in almost all the wires. But interestingly, when you reverse the current direction, you can see that the displacements are smaller, except for the first wire. And you can only see them in two of the wires, three of the wires. If you do a more systematic study, you can see how this depends on the angle. And you immediately notice that there's a big asymmetry between the two current directions. So this, you can see this in terms of a nonlinearity. Okay? Positive current and negative current do not have the same effect of domain motion. This means there's something nonlinear. But the talks themselves, they're linear in current. So the only nonlinearity can occur due to a distortion of the magnetization by the current, such as a domain wall, in our case, a domain wall tilting in the wire, or canting of the domain wall magnetization with respect to domain position. So these are the two hypotheses we have, which we are going to test now. So for the first one, what we did is that instead of making these discrete wires, we made pads, and we nucleated like bubble domains inside, so we have circular domain walls. And when we apply current, we saw that one of the domain walls is moving mostly to the left, the other one mostly to the right. But similarly, this is equivalent to this case, if you just sort it by 180 the sample. So what we understand from here is that you don't have any tilting of the domain position, because here domain walls cannot tilt because they're so long and they don't have free ends. Okay? So you must be due to canting of the domain wall magnetization inside the domain wall. So a way of understanding this is based on André Thiaville's model of DMI and SOT. Just a brief reminder. So the spin-orbit torque acts as an out-of-plane magnetic field, which is proportional to the component of the magnetization aligning the current. Okay? So if you have block walls, there is no effect. But if you have DMI, this will make nail walls, homochiral nail walls. And in this geometry, the magnetization is parallel to the current, so the spin-orbit torque is very efficient. Okay, so what happens if you have a bubble domain wall, like this, a round one? Okay. Now the DMI will point towards the center of the bubble, let's say. Okay, so does the magnetization of the layer. So when you apply current, the current creates an out-of-plane magnetic field proportional to mx and parallel, which creates a torque. And these torques, they create a distortion of a domain wall magnetization, which is here in red. So as you can see, if you have a distortion, then it's no longer this guy that goes faster, where the mx is maximum, but it's this guy. So then the velocity you would expect to be higher at a certain angle. Okay? And this is actually what we observe. But this is not all. Because this distortion you would only expect to have at high velocity, because this is the dynamic effect. Okay? If you slow down, you're not supposed to have this distortion. This should only be when you go fast. So we tested this. And we varied the current density by roughly a factor of 2, which modifies the domain wall velocity by 3 orders of magnitude. And interestingly, we see that the angle where we see the maximum domain velocity stays the same. So we believe that this is, I mean, we don't know what it is, but we believe this is beyond the IWST model. And so far we have no explanation for it. Nevertheless, we wanted to make use of it and see if we can apply this phenomena to magnetization switching. So for this, you can imagine that you have 3 different wires. You can cut your path into 3 different parts. One which goes vertical. On this one, you will have both white and dark contrast, which means that both domain walls can propagate by current. And you can also look at the one pointing to the left, where you only have white contrast, so meaning that only one of the domain walls can propagate. And the other one, you only have dark contrast, so only the other domain will propagate. So now if you want to make devices, you have a way of propagating domain walls, and you have a way of selecting domain walls. By changing the angle of the wire with respect to the current. Okay? And you still need one more ingredient, which is domain wall nucleation. Okay? So for this, it's actually very simple. It is enough to trim this wire into a triangle, and then because you have this much narrower part here, you lose some of the thermal stability, so you know when you apply current and everything heats up, you know where nucleation will take place. So now if you want to switch, for example, from dark to white, you put together 2 wires, triangular one and a straight one, and the nucleation here will be able to propagate in a straight wire. If you want to switch in the other direction, you put together differently tilted wire with a straight wire, and you get your switching direction. If you want to make a bipolar switch, you rotate this guy by 90 and have it together, and you have bipolar switching. Positive current switches black to white, negative current white to black. Okay? Another thing you can do is that you can turn everything by 90 degrees, 180 degrees, sorry. And now you get 2 bipolar switches which have opposite polarity. Just by modifying the geometry. So what about the experiments? We made these structures, and here you have the SEM image and the differential curve imaging showing the initial states of the magnetization before we excite with current. You can see that after applying current pulses, positive current switches one of the objects, negative current switches the other object. It is the opposite case when you change the initial state. So this is perfect bipolar switching. Interestingly, you can also have mid states when one of the magnet is pointing up, the other one pointing down, and they both switch together in the opposite direction. So now we know this works, and we can also check if it works through the same mechanism that we expected. And for this, instead of applying the 8 pulses all together, we separate the pulses in series of 2 and take images after each pulse. And you can see here that the contrast always starts appearing from one end and propagates through the wire, depending on where the current, or the current direction. Okay, so always it's in the direction of the current. Okay, so now this is a switching mechanism where you have shape control magnetization switching, but you still have the current that tells you where it's going to switch. You can also make devices where the switching is independent of the current direction. Okay, and this is what I'm showing here. So instead of making U-shaped devices, you can make S-shaped devices. So the straight wire has 2 ends which are tilted in the same direction. Here's an example of the initial state of the wires and the effect of the current. You can see that positive, negative current both switch the same object if you initially saturate it dark, but if you change the initial state, it's only the other object that switches. So this is a kind of reversible switching. And of course, this also happens through the same mechanism of nucleation and propagation. Now, I would like to convince you of the importance of the ability to control the switching by shape by an analogy with the semiconductor industry. Okay, you have a microchip. Microchip is composed of many elements, including logic parts and different memories. And they all made of transistors and interconnects. And the only thing that differentiates these is the shape. Some of them are larger, some of them are smaller, are denser, or faster, but ultimately it's a design process when you draw shapes that differentiates it. Okay, and this is what I think we have here. We have an example of the same concept applied to magnetism, where you can make different magnetic memories on the same chip, just by changing the design. Okay, not by changing the material, not by changing the process, just the design. And if you want to compare it now to an existing memory, we decided to compare this, like an estimate of how much this can be useful compared with SRAM, for example. You know that the switching of SRAM is way below the nanosecond. Okay. So the physical limit of the switching speed for these devices is actually the domain mode velocity. Okay? So you want to have an object that is sufficiently larger than the domain mode width, so this process still applies. But the smaller it is, the faster the process. If you take a limit about 50 nanometers, which is roughly 10 times larger than the domain mode width, and you consider the domain mode velocities we've measured for this kind of materials, you get a switching speed of the order of SRAM. And if you consider integration and scalability, for example, you know SRAM has a very large memory cell because it has many transistors. And this kind of three-terminal device should work with two transistors. So if you consider just the surface area, you can realize that this can work, can be competing with SRAM until a 7 nanometer feature size, while keeping the advantage of being non-volatile, which is very important. So in conclusion, we propose a new way of ionization switching to show that we can obtain zero-field SOT switching in platinum colored aluminum, which is by itself important. This is based on non-collinear domain mode. We design both reversible and reversible switches. And for the perspective, I would say the most important area is that this is a generic method, okay, which is independent of the SOT mechanism. You can apply this to any kind of materials where switching is controlled by in-plane current, even topological insulators or spin hole, rush bar, anything. So thank you for your attention.
Thank you very much for a very interesting presentation. So we have more.